Imagine a chemical so strong their nickname is Forever Chemicals. They can be found in rainwater, in soil, in aquatic life, and even in human bodies all across the world. If you can think of the spot, then they will be there. These chemicals are known as PFAS, or per and polyfluoroalkyl substances that are well deserving of the nickname Forever Chemicals. So, what if there was a way to be able to take these once impossible and indestructible chemicals and actually destroy them once and for all? Well, there is, and in today's podcast, I'm going to go in depth on the new treatment technique that could change how we deal with PFAS contamination. First, I'm going to talk about what PFAS are, then why they're such a massive environmental and public health problem, and lastly, how a new technology called sigma pyrolysis may offer a promising solution to end this problem once and for all. PFAS are a large class of synthetic chemicals that have been widely used since the mid-20th century. Becoming popular in the late 1940s and early 1950s, they were known for their resistance to being broken down. Later, we tragically discovered their ability to accumulate in almost everything, including the physical environment and living organisms. In terms of chemistry, PFAS consists of long chains of carbon atoms bonded to fluorine atoms and often ending in various functional groups. The physical composition is a key reason why they are so persistent, which comes down completely to chemistry. The carbon-fluorine bond is one of the strongest covalent bonds in organic chemistry. Because fluorine and carbon have a high electronegativity difference, this creates a very strong bond that is very stable and resistant to heat. The chemical stability is exactly why PFAS was so widely used commercially for so many years. PFAS was first created in 1938 when Roy Plunkett accidentally made Teflon. Its non-stick heat resistance properties made it revolutionary. Soon, PFAS were used in non-stick cookware, firefighting foams, food packaging, waterproof clothing, cosmetics, and industrial lubricants. But the same chemical stability that made PFAS so useful also made them nearly impossible to break down once released. By the 1970s, scientists were detecting PFAS in human blood and environmental samples. By the 1990s and early 2000s, it became clear that PFAS were linked to serious health concerns, including immune disruption, developmental effects, and certain cancers. Today, thousands of PFAS compounds exist, and scientists are still looking for ways to develop cost-effective methods to destroy them. Destroying PFAS isn't as simple as filtering them out like other contaminants. This is a huge issue in wastewater systems because PFAS accumulate. Traditional wastewater treatment only concentrate PFAS into sludge rather than destroying them. The sludge, also known as biosolids, has historically been spread on agricultural land as fertilizer. This is a major problem because PFAS-contaminated sludge can spread these chemicals further into soil, groundwater, crops, and eventually human drinking water. In the past, scientists tried incineration to destroy PFAS. However, incomplete combustion can generate harmful byproducts and release PFAS into the air. Because of the strength of the carbon-fluorine bond, extremely high temperatures are required to truly break the PFAS molecules apart. And this is where pyrolysis enters the picture. Pyrolysis is a thermal decomposition process that heats material to a high temperature in the absence of oxygen. Pyrolysis can convert organic materials such as plastics and biomass into smaller molecules, gas, oils, and biochar. Sigma pyrolysis is a specific patented temperature-controlled form of pyrolysis designed to treat wastewater sludge and destroy PFAS. First, the wastewater sludge is collected from a municipal treatment plant. The sludge then undergoes biodrying, where biodryers use heat generated from microbial activity to reduce moisture content. Next, the dried sludge is placed into an oxygen-free chamber and heated to a temperature exceeding 1,000 degrees Celsius. At these temperatures, organic carbon-carbon bonds break, and more importantly, the extremely strong carbon-fluorine bond in PFAS are cleaved. In a pilot study, it was reported that pyrolysis processing removed approximately 97.4% of PFAS from biosolids. To make this process safe, any remaining gas are treated through thermal oxidation systems to prevent atmospheric release. One of the most innovative aspects of Sigma pyrolysis is the closed-loop energy design that allows heat production during process to be reused in the biodryer system. This significantly reduces external energy demand and creates a system that approaches almost net zero energy consumption. This process also produces biochar, a carbon-rich solid that could potentially be used as a soil amendment. So not only does Sigma pyrolysis reduce PFAS concentrations, it also transforms waste into a usable material. Despite its promise, Sigma pyrolysis is still relatively new. The first full-scale installation by Biofortech was established in California in 2017, and adoption has been limited geographically. There are still questions regarding scalability, long-term emission monitoring, cost, regulatory acceptance, and the fate of all fluorinated breakdown products. No technology is perfect, so careful oversight will be necessary to ensure the process completely destroys PFAS rather than transforming them into new persistent compounds. In summary, PFAS contamination represents one of the most significant environmental challenges of our time. However, with technologies like Sigma pyrolysis, we may have a way to fight this problem. PFAS were designed to resist degradation and they've succeeded, but we cannot let PFAS win this fight. Sigma pyrolysis represents one of the first technologies designed not just to manage PFAS, but to actively destroy them. While further research and wider implementation are still needed, this approach could mark an important step forward, reducing long-term environmental contamination and creating a healthier future. If we are going to solve this PFAS crisis, we need technologies that can match the strength of the carbon-fluorine bond. Sigma pyrolysis may be one of those technologies. Thank you for listening to my podcast.